ठीक है, ये कॉन्सेप्ट तुम्हारे पास है, अगर तुम मेरे ऊपर फेंक दोगे पता यार, नहीं यार तो पता नहीं हर बार 100% मैं भी नहीं कर सकता। हो सकता है ना मेरा 70% वाली अच्छा हो 20% मेरे लिए तुम्हारा 10% मेरे लिए भाई पढ़ने लेना क्या है कि मुझे बहुत रहता है मैं पढ़ा ले लेकर ये देख लेते हैं तो हम बना के मुझे सिखा देता है मुझे बना ले ये बना ले भाई पहली बार पहली बार
So we will start at 6 5. We will wait for other learners to join. So let us start. Hello, hi, namaskar. I'm Prashil. I'm a Prime Minister's Research Fellow at IIT Mumbai, and here we are learning advanced thermodynamics and molecular simulations. So this is our live interaction session number 10, where we will be discussing the portion that we have covered in previous weeks, and we will be solving some of the questions, right, that are there in the assignment, which will be helpful for you to solve the questions in the exam, right? So let us start the session of the day. So the subject is advanced thermodynamics and molecular simulations. So we have divided that subject into two parts: thermodynamics, right, where we have talked about basics of thermodynamics and then statistical mechanical approach, and second part was the molecular simulations, where you will be using some concepts that we have learned in statistical mechanics, so that we can apply that thing to molecular simulations, and we can do some computer simulations to get some properties of any material of our interest, right? So Correct. Here we learned molecular representation, molecular representation of system, and modeling, right? What we were doing is something called as modeling. We were having some conditions based on which we were saying, okay, this condition should be satisfied by the particular equation. And we were applying some laws of science, I should say. It could be mathematical laws, it could be statistical mechanical laws, right? And then second part is practical applications, right? So here what we used to do is, right, we did mathematical modeling. So those models are basically some equations that represents our system, right? So those equations has sometimes could be some algebraic equations, some uh, differential equations or partial differential equations, right? So when it is a simple equation, then we can easily solve on pen and paper, right? So simple equations which can be easily solved, or we were taking some simple examples so that we can understand what is happening, how those models are representing our system, and we can simulate, we can add some parameters, we can add some numbers to make some sense out of those values or some outputs of the results, right? So simple, or sometimes it is complex equations, right? Equations are complex, could be differential equation, and we need to solve them simultaneously, right? So accordingly, we might need computer programming based approach, programming based approach, right? We need programming based approach to solve the equations. And that's where we are saying this is something called as practical applications. Now, how simple your system is, or to the extent you are doing the modeling of the system, you can add complexities in it, right? And we can solve those things, right? So using simple example, we can understand, okay, whether the modeling based approach that we have adopted is correct. And then over the period we add some complexities, and then we see, okay, yes, indeed it is also able to predict the properties of a complex systems. Now, to give you an example, if there are two particles, or I should write, I have a system, it has some particles. I want to calculate what is the interaction energy of the system. You know, the total interaction energy is the sum of kinetic energy plus potential energy, but when the temperature is constant, this kinetic energy is equals to half mv square, which is also equals to 3 by 2 nkt, right? So this is how it is. So whenever the temperature is constant, we are saying, okay, kinetic energy is something that is independent, and then we'll just calculate potential energy, which is also called as configurational energy. Configurational energy, and the sum will give you the total interaction energy. right? Sum will give the total interaction energy. Now, what are the different interactions that might be there between two particles? Just think about it. How many sort of interactions are possible between particles in a system? So I have a box which has particles, and now you need to tell, okay, what are the different types of interaction energies that are there. So we'll start with simple things, and then we will keep on adding the complexities, right? And I'll tell you how can simple systems be can be used initially, and then adding complexities will help us to get m- more and more accurate values of property that we want to predict, right, for a given system. Okay, so let me know. Think about it. What sort of interactions are possible? So whenever you want to calculate an interaction energy, you need to first of all think what sort of interactions are possible. The simplest interaction energy is assuming that there is no interaction between the particles, right? So I have two particles. Irrespective of I am changing the position of this particle, nothing will happen to this, right? So there is no influence, right? For example, I am a person who is standing here some at some location on earth, and there is moon over here, right? So there is some p- person who is on the moon, right? I don't have any interaction energy with it, right? Because the distance between these two particles is very 2%. So there is one person who is here on earth, and there is another person who is there on moon, right? So you can imagine that there is no interaction between the particle. Whatever this particle is doing or this person is doing over here, it has nothing to do with what that person, the other person, is doing on the moon. So there is no interaction. So simplest interaction energy that we can assume is no interaction. That is no interaction. Then you can say no, up to certain distance there is some interactions, and after crossing that distance there is no interaction, right? So in that case, you can see there are different models, just like what we studied in the class. For example, hard sphere model. What does this model tells? Okay, I have two particles, one particle is sitting here, other particle is sitting over here, right? There is no interaction between these two particles up to certain distance, and as soon as the distance is zero, that means when they overlap the distance is infinity, otherwise there is no interaction. This is called as hard sphere model. But in reality, you may know that there is some interaction between two particles which are at some vicinity distance r, versus this is u of r. So in that case, you can have some different potential. For example, square well potential. Square well potential. They say. What does the square well potential say? There is no interaction between two particles. You can see interaction energy as a function of r. I am plotting, and this interaction energy is equals to zero up to this distance, and for certain distance there is this interaction energy, that is some epsilon value, and then as soon as it reaches this distance, see the value goes to infinity. So what is happening, you can see this is allowing some interaction between the particle, but beyond certain distance, when the particles start to overlap up to certain distance, you can see how up to this distance, which is called as the diameter of the particle. Diameter of the particle, the interaction energy goes to zero. That means this model specifically, that is called as square well potential. Square well potential, that means it allows particle to interact up to certain distance. It allows the particle to interact up to certain distance. Beyond that distance, or I should say, that distance is referred to as sphere of influence. Beyond sphere of influence, interaction energy is equals to zero. Interaction energy is equal to epsilon, and interaction energy is equals to infinite. Interaction energy is equals to infinite when the distance between particle is less than the diameter of the particle. If it is less than the diameter of the particle, then the interaction energy is equals to infinite. That means it allows the molecule to interact up to certain distance, and beyond that, interaction energy is equal to zero, and it also prevents the overlapping of two atoms, because you know that up to certain distance, if I want to put this atom, right, they cannot penetrate, they cannot go inside, right? So that's what people would have thought, and they mathematically said, okay, this is how it is. But then what is the problem with it? First model that we have seen over here, this shows that there is no interaction. Where did we see this? When there is no interaction between two particles, you can see this is the assumption, this is the thing that has been taken from ideal gas equation, right? We know that there are particles at specific distance, they are not at all interacting with each other. So this sort of assumption is the ideal gas assumption. Hard spin model, what does this say? So we are saying, okay, there is specific r, there is specific r, right, which is not been crossed by two particles, right? They can, if they touches, then the energy is infinite. That means which is not possible, which is not possible. And if it is zero, that means up to certain distance d, there is no interaction, and as soon as the distance is d, the energy goes to infinity. Energy goes to infinity, and this d can be any value, it can be zero, just like what I have plot over here, where you can see d is equal to 0. That means there is no diameter to the particle, and as I move, as I model it accurately, you can see there will be some diameter to the atom, correct? There will be some diameter below which the particles cannot go, right? And then we had seen third one, this one is third one, right? Here what we have seen, in the hard sphere model there was no interactions, right? As soon as they touch, the energy value is equal to infinity. That's called a hard sphere model. But we know in reality there is some interaction, and in van der Waals equation of state we have calculated that. We have assumed that there is some interaction up to certain distance, and that's where you can see this is the zone where there is interaction is there. Here there is no interaction and there is no penetration below the radius. That's what we have clearly mentioned in point A, B, and C. So this is good, right? You can do any sort of interaction energy calculation using these models. What is something that is missing? You can see when I am writing this equation, third one, it is not continuous. It is not continuous, right? We have three different conditions which are telling, okay, up to certain distance this is the value, beyond this distance this is the value, and so on, right? So we want a continuous equation because we will be solving Newton's equation, right? Newton's law of motion, which tells you force is equal to mass into acceleration. Now this differential equation, while solving, we need to ensure that this is a continuous equation, which is not the case over here. It is discontinuous, right? And that's where we want continuity, and here we will be converting into something called as van der Waals potential, right? Instead of having equation like this, it goes to infinity. So instead of having equations like this, or equations like this, right, we have fourth equation which is continuous, right? At particular r value we will get what is the value of u of r, that is interaction energy, u of r, correct? U of r. And this interaction energy is then in used in two schemes to integrate and get the new position, because a particle is at a particular location, it will move to some other location, and I want to calculate, okay, how that movement is happening. And in equilibrium, when the movement is happening around a constant mean positions or within a system, it will give rise to some property. It will give rise to some property. That property we need to calculate, right? That property we need to calculate. So there are two ways. One is called as Monte Carlo, other is called as molecular dynamics, that is MD. This is MC and this is MD. So two approaches we adopted to get these things. Now, just like I told you, we have a system and I have a particles in the box. So when you want to study any systems, you have to generate particles. It will be having positions, right? Those positions are randomly generated such that there should not be any overlap between particles. That means at a particular position, there has to be only one atom. There has to be only one atom. If there is overlap, what will happen? The distance between two particles is equals to zero, and if it is equal to zero, you know the interaction energy will be infinite. That's what we need to ensure while generating the numbers. So for one particle, there is xyz coordinate. Similarly, for n particles, there will be 3n coordinates or variables which will change over the period. Right, this values will change, and we need to sample it using Monte Carlo and molecular dynamics methods, right, such that after reaching certain value of, right, reaching we will be reaching equilibrium, where we can see density of any state is independent of the time. That means if I'm moving ahead in time, if I calculate new positions every step, right, I'll move to next position, again to next positions, and with respect to time I'll get some positions, and I'll see that the system's energy is not changing, or the particles are systems energy. That is what is one of the way to predict whether the equilibrium is there or not, right. We'll calculate the energy, or we'll calculate some other property, for example density, right. Initially I have system with some particles in it. I know these are randomly filled, and if I do simulation over the period, I'll get new positions, and then I'll get density. Density is equal to number of molecules per unit volume. Volume is also changing with respect to time, and this density, if it is not changing and matches experimental results, then I'll say okay, I need to stop my simulations, and that's how I do simulations termination, right. So now, just like I discussed, there are two ways: Monte Carlo and molecular dynamics. In molecular dynamics, what we do, we have some position x. I need to get x at t plus dt. So this is my x at time t, and I want to get x at time d plus dt. How will I get it? I'll calculate what is my interaction energy u of r using any potential that I have mentioned over here, right? There are multiple types of potential. I have mentioned only four over here. Using that, you know the distance, right? You know some parameters that are required, for example diameter of the particle, that is available in the literature, and then you calculate interaction energy. You also calculate force, that is what is du by dr, and based on that force you will get x at t plus delta t is equals to x at t plus of, right, velocity will be there, that is dx by dt. This is rate into that particular value, right, into delta t. So we will get in delta t time how much displacement has happened, and this to get dx by dt, we know force is equals to mass into acceleration, which is equals to mass into dv by dt, or which is equals to mass into d2x by dt2. So this value, and then there will be next term, right, d2x divided by dt2 delta t square. You do this t plus delta t, t minus delta t, and you will arrive at some equation, for example central difference, where you will just need 2x by dt2. How will you get? You know the force, you divide by mass, you will get the acceleration. That acceleration you substitute, you are going to get the new positions in future, new positions in time. This is the way we do molecular dynamics simulations. Now what about Monte Carlo? In Monte Carlo we are not following the time, that's why it is a probabilistic way. What we do, I have a system, random position of particles, and then I am moving from one, I'm moving one of the particle from location 1 to location 2. So this is my location 1, I'll move to location 2 and I'll calculate what is change in the energy. You know, at first position when I was at this location, one is the interaction energy between the particles of the system. Second is u2. I'll take delta u, which is u2 minus u1, and I'll see whether this delta u value is acceptable or not. So what we know from undergraduate thermodynamics, that the energy of the system decreases to increase the entropy, and here also in the class we have proved that. We have proved that value. Correct? u2 minus u1, right? So delta u is there. If delta u is negative, we will accept, because that is what is thermodynamically favorable. Accept. But if it is the other case, that is positive, we should reject it. But instead of rejecting, we are accepting it with some probability, rho of new state, which is equals to n new divided by n old, which is equals to exponential minus of delta E divided by kBt. As the magnitude of delta U or delta E increases, the probability by which I'll accept will decrease, right? Will decrease. So there will be curve like this. If the delta U value is delta E or delta U is negative, I'll accept it with the probability of this. And as the value of delta E increases, I'll not reject the move, I'll accept with lesser probability. And I'll check whether that move is acceptable or not. I'll randomly generate a number, right? So this is the value that is given by this equation, which is called as density, probability density. That probability density will give you some value, and I'll generate a random number, and I'll say, okay, this is my safe zone under which there will be acceptance of the move, rest will be something that is unacceptable. Depending on the value, my acceptable zone volume will decrease, the volume of the acceptable zone will decrease. And then I'll generate a random number, and I'll see whether that random number is here or here. If it is below the limit, I'll accept. If it is above the limit, I'll not accept. And you can see, as the value of n increases, this zone decreases, right? That means I have lesser and lesser probability to get the number in that zone, so I'll accept it with some probability. This is how it is the case, and this is given by the metropolis criteria. We use detailed balance, metropolis criteria. We got it using detailed balance, right? And we get the new positions with respect to time. With respect to time. Then what we did some small experiment, computer experiment, right? We calculate something called as mean square displacement, MST. How a particle is moving away from its mean position that we have calculated. How a particle is moving from its mean position with respect to time, and that will give you the diffusivity of the particle. Diffusivity of the particle. Can anybody summarize that part or any idea about it? Please let me know. So we were using metropolis criteria, which tells you the definition of whether the movie is acceptable or not, right? So whenever I'm getting the interaction energy at point 1, I can use any equations as I mentioned. That could be Hardspear model, or it can be square well potential model, or fourth one, which is LJ potential. These equations will give you these equations will give you interaction energy as a function of distance between two particles. So here I have particles at different positions. I know what are the coordinates of this particle: x, y, and z. And then there is another particle over here, x, y, and z, right? X, y, and z. And if I know, I can calculate what is the vector distance. R is equals to generalized formula I'm writing, square. So this will give you the value of R, and this R can be then substituted into the equation. For example, I am writing for LJ potential. Sigma equal to 1, epsilon equal to 1. Now, if I am giving you this parameter, so sigma stands for diameter of the particle, diameter of particle, and epsilon will give you strength of interaction between two particles. Or when we want to compare it with experiment, it is called as polarizability. Polarizability. Polarizability it will give. So these values I have given. Now you just need to get the value of R, substitute here. You are going to get U1, right? You are going to get U1. Then similarly, when you displace a particle from its position, you will get U2. You take the difference, that difference value is this. If the difference value is less than 0, that means it is negative. We know the energy of the system has decreased, that means the move has to be accepted. If it is positive, we have to accept with certain probability. Not all moves will be accepted, that we get from the detailed balance. That we get from the detailed balance. Correct? And we will calculate this delta U as a function of time, or number of Monte Carlo steps. Better to represent in terms of step, and we will see that delta U is decreasing and it is constant and fluctuating around a point, and that's where we say that okay, now the system has equilibrated. So this is called as equilibrium, right? So this is the system which is equilibrated, right? And this is the process by which we are reaching the equilibrium. So this is, I should write as the equilibrated state, which can be used to get some properties of the system. So what we did, we had simple model, like hard sphere model. We have added complexities, right, to get more and more realistic system, which will give you the interaction energy forces, and those can be used to get the new positions. Till we do this till we reach equilibrium, till we reach the equilibrium. That is what is the purpose. Then, as I said, we used this to get the position of the particle, and that from that position you can get multiple properties. For example, mean square displacement about mean square displacement, that means displacement around a mean position, which will give you diffusivity of the MSD x minus of x naught whole square, that we will calculate as a function of number of steps, and then it will give you diffusivity of the particle. If it is moving a lot, then the diffusivity is high. If it is moving slower, then it is having lesser diffusivity. That is the property of a system we can get using this sort of simple experiments, which are computer based experiments. We do not need to do any experiments in lab. So now with this background, we will solve the questions, and we will discuss some of the parts that we have covered in previous classes as and when required while solving the questions. So there is question number 1, which is on your screen. For that, we need understanding of molecular simulations, right? Or you can say the mean square displacement concept is required. So question number 1 is on your screen. Deviation from linear behavior in the plot of mean square displacement versus Monte Carlo steps, just like what I have drawn here. Mean square displacement versus number of Monte Carlo steps. So what we do, for example, I have a particle which is moving like this. I'll not draw a box over here. I'll just say, okay, this is my particle which is moving in time. Right? It is moving in time. So if it moves in time, I will calculate what is its deviation from the mean position, that is previous position. So first my position is this. I will see that there is no displacement that has happened around this. So I'll just consider this x direction motion, 1D motion. You can see up to this point there is no change in its position. It is just moving, but okay. So this is my x direction. Then I would write this is my center. It has moved this many distance in one step. Next step, my reference is this. I will calculate, okay, this is the displacement, third from this to this. So in each step that I'm going, I'll consider previous step as the distance, and I'll calculate what is the distance that the particle is making. Distance that the particle is covering, right? Then I'll go, I will have this as a reference. Then I'll take two steps. So this is my step 1, this is my step 2. So in first step, this is my reference, right? This is my new position. In second, this is my reference and this is my new position, right? That's why it is like this. So I'll take two steps that we have discussed in the class, right? We will take two steps, and then I'll calculate what is the deviation, right, with respect to the initial position, which is reference position. So I'll see, as I'm increasing the time, the displacement from the mean position increases, and that's where I'm going to plot mean square displacement as a function of Monte Carlo steps. It could be m steps, right? One step, two step, three steps, and you will find that okay, it is increasing with respect to time, right? So that from the slope we can get 4 dt is equals to mean square displacement, and mean square displacement x minus of x naught square, which is equals to 2d dt. This is 2 into d into dt. So t is something that relates to number of Monte Carlo steps m, right? This d stands for dimensions. Right now I'm considering movement in only x direction, so dimensions is equals to 1. Dimensions is equals to 1, so this is 2dm, it's equals to msd, right? So msd divided by msd divided by m is equals to 2 into d. So from the slope I am going to get what is the diffusivity. So this experiment is going on, right? I am doing multiple samplings. The particle will move to what and all locations it wanted to go. So the deviation from the linear behavior in the mean square displacement, so you can see here it is somehow linear motion is there, somehow linear motion is there with respect to time. You can see msd is equals to 2d dt. So you can see here msd is proportional to t. Msd is proportional to 2. So this is my linear behavior. So there is deviation in the linear behavior in the Monte Carlo steps. So in the graph, right, mean square displacement plot, which results from, so first point is written poor averaging for long trajectories. Poor averaging for long trajectories. So for example, now what I'm doing, I was taking one step, two step, three step, and I was calculating what is my MSD. If I do not do sufficient simulations, I need to go up to 1,000 or 10,000 steps. But if I do not do sufficient simulation, then what will happen? There will be poor sampling for longer trajectories, right? You can see as I increase the number of steps, right, m steps, if I was taking, if I'm taking only one step and calculating how it is moving, I will see I'm having more number of data points, 1 2 3 4, right, to get what is the deviation from the mean position. This will keep on decreasing, this will keep on decreasing as I increase the number of m steps, right? If I take 2 steps, then numbers will be lesser. If I take 3 steps, again it is lesser. So similarly, if I do n by 2 if I go, right, the number of sampling points will decrease. So for example, if I draw like this, after 50% the numbers will go keep on decreasing, and that's where there is poor sampling for trajectories longer trajectories, right? If I increase the value of m, the number of data points decreases. That's why there is poor sampling for longer trajectories. That means for higher values of m, sampling will be poor, and that's where the deviation will occur. One of the reason. Secondly, I am saying every particle is moving and there is collision with other particle. So delta t is the time of collision. If my time is less than delta t, that means collision will not happen. Collision will not happen. If the collision will not happen, then it will move with rectangular motion. That means it is having time is equals to distance upon speed. So time is proportional to distance. That means t square is proportional to distance square. MSD is basically what? X minus x naught square. That means it is r square. So here you can see it is not linear. This is r square. Like this curve will be there. So here it is MSD means r square proportional to the t. This is what is the square thing. And when I do rectangular motion, you can see distance square. That means r square is proportional to t square. That means it is a linear motion. So before the collision, there is this linear behavior where there will be molecule which will be moving, and it will be performing rectilinear motion. So that's why there will be deviation from the theoretical value. Then if you use fixed case, fixed boundaries, that means I have a box and there are particles. If they collide with the wall, they will come back. That means we are not allowing the particles to go out of the boundary. We have, and if you have very small box, then if you use a fixed boundary condition, multiple collision will occur. As we decrease the box size, the collision will be higher and we will deviate from the, we will not allow the particle to move based on what or how it wants to move, and there we see deviation from the mean square theoretical value, MSD theoretical value, right? Third and fourth point, what it says, if I have a box like this, instead of periodic images, if I use something called as MIC, that we'll talk about, right? MIC, minimum image convention. If the particle moves to the next box, another particle is here, what is the minimum distance between particle? This particle has moved over here, its image will come over here, right? Somewhere here. So the minimum distance is this distance, and if I do not take PBC using minimum image convention, I will be have to take this distance, which is the larger distance, right? Which is the larger distance, right? So using the trajectories within the simulation box when using PPC, and if you do not allow box, the minimum image convention to be there, then energies will be wrong, right? So there has to be PPC and we should consider the minimum image conventions, right? And if we are not following that, then there will be deviation from the ideal behavior. There will be deviation from the ideal behavior. So this is about question number 1. Then number of m step trajectories available from Monte Carlo simulations for number of steps are n, and m is what? M is m steps trajectories. So I'll just give you simple example, 1 2 3 4. If I take 0 1 2 3 4, if I take one step trajectory, how many trajectories are available? This is 1 2 3 and 4. One step is equals to 4. If I take two step trajectories, that means this is my two step trajectory number 1. I'll start from this location, number 2, number number 2, and then number 3. Two step is equals to 3. If I take three step trajectories, then see, only 1, and this from here it is 2, correct? And four step trajectories here is equals to 1. So I can have large number of n steps, capital N steps, and m is something is, this is what is m step. So if I want to calculate m step, then there is a formula, m minus n plus 1. Now just substitute the value. If I want to calculate for this, that means m step trajectories. So number of, this is equals to number of trajectories available. Number of trajectories available. So 3 step trajectories, m equal to 3, minus number of steps is equal to 4 plus 1, which is giving you 2, right? So this is what is the formula we have discussed in the class, right? And I have also given you this example. Similarly, you can calculate for any number of steps, any m steps trajectories available, right? So formula is this, n minus m plus 1. Option number C is correct. Now number of images when using periodic boundary condition, we know this is a PPC system. If I apply PPC, that means we have infinite images of our system, and overall we see this is very big system. So infinite number of images of the particles are available when we are taking periodic boundary conditions. So within a small range system we are simulating, and we are getting a bigger system that is possible. In programming, what is floor represent? So you can get a clear indication. You just need to go to the Python code runner. Online also it is available. You just need to type what is floor 1.6. It will give you some value which is 1, right? What does this do? Option A is correct, but what does this do? Floor is giving you the lowest possible integer. Lowest possible integer. Now you don't need to mark up these things, right? It changes with the programming language. It is floor, called as floor in some language, it may be called as some other uh, it will be represented as some or named as some other function, but the function will do same work. So for Python 1 point, this tells you 1. For example, if I have floor of, if I calculate 2.3, 3.2, 4.6, what it will give? It will give you the lowest value of integer. So this is 2, this is 3, this is 4. Similarly, if I calculate floor of minus 2.3, minus 3.2, minus 4.6, the lowest integer is minus 3, minus 4, here it is minus 4, right? So this is how lowest integer that is being written by the floor. So here you can see lowest integer is 1. So option A is correct. Then in programming again, what does this represent? This represent modulus operator. You can test it using programming in Python. Modulus is something that returns the remainder when doing the division. For example, modulus of 30 modulus 3, that means 33, if I do 30 will be there 0, so remainder is 0, so 30 modulus 3 is equal to 0. Similarly, if I do 15 modulus 2, that means 15 will be here, 2 will be there, 7s are 14, giving you 1, so remainder is 1. So this remainder is written by this operator. Now similarly 3.4 minus, right? And if I do like this, what will be the remainder? 2 ones are 2, 2 twos are 4, right? Lower value we have to take to subtract. So what is the value? Minus of 2, minus again, so this is what is plus, minus 4 has to be subtracted from, so this is minus 3 minus minus of 4, which is giving you minus 3 plus 4, which is equals to 1.6. No, this is what is 0.6. 3.4 has to be here, 3.4 has to be here, correct? 4 minus 3.4, it is 0.6, so remainder is this. So option D is correct. Option D is correct. 0.6. Please let me know if you have any doubts. These are some simple examples. You can get explanation on some internet sources as well. And specifically, I would suggest you should try this in programming, so that for multiple values you can calculate using handwritten hand calculations, and then you can compare with the Python code. Now, number of three body energies needed to compute for 6 particle. So we know if I'm having a system which has 4 particles, how many interactions will be there? 1, 2, 3, 4. One particle 1 will interact with particle 2, particle 1 will interact with particle 3, particle 1 will interact with 4. Then particle 2 will interact with particle 3, Particle 2 will interact with particle 4. Particle 2 will also interact with particle 1, but that has been already counted. Similarly, particle 3 will interact with 4. So how many combinations are there? 6 pairs will be there. And what is the shortcut formula? N, capital N, C, N body interactions, and this is the total particles. Now you calculate what is the value for 6 particle 3 body interaction. So it is 6C3, which is equals to 6 into 4 into 3, no 6 into 5 into 4 3 times, and then 3 into 2 into 1. So what does it gives you? 20, right? So 20 interactions will be there that needs to be computed using the model which has 3 body interactions and are having 6 particles. So these many interactions we need to calculate, correct? One interaction with 2, interaction with 3, one interaction with 2, interaction with 4, and so on. We don't want the repeated interactions, correct? Now question number 7. Equilibrium is established in Monte Carlo simulation. We discussed, right? We calculate the delta U, that is interaction energy, with respect to number of Monte Carlo steps. We calculate the interaction energy between the particles, that is what is U. Then we calculate U2 up, which is the interaction energy when particle is moving at some other location. We calculate what is delta U. This delta U has to be plotted with respect to number of MC steps. So this is one step, delta U 1, second step, delta U 2, and so on. We'll calculate and we'll find that interaction energy decreases and it reaches and fluctuates around a constant value. That means around the average value, that is E bar, the value fluctuates. Fluctuation above the average are almost same as the fluctuation below, right? Below the average value, above and below the fluctuations are there. Instead of above and below, I'll say okay, that is fluctuation after running reasonable number of steps. So this is how it tells you whether we have reached equilibrium or not. Then short range interaction between two particles computed in Monte Carlo simulations using periodic boundary conditions. Using what we do, we calculate minimum image convention. We use minimum image convention, just like this is my system, particle is here, other particle is here, the particle has moved to this location over here. So then particle will come. So this is my blue particle, I should write blue, right? And then this is my black particle at its location. The other particle will come here, right? It has moved to this location, example. So the particle will, other particle will come here. This is the image of this particle, correct? So now what is the minimum distance? This is the minimum distance, right? Here also there will be one image over here. This is also the distance. So which distance we need to consider? We need to consider this minimum distance. And how do we get that minimum distance? We have to sit on the particle and calculate what is the smallest distance. So coordinates or particle in the simulation box with center of mass of two particles as the box center. So here the option will be fixed spaces. No, we want it to be have a new distance, new positions, relative. So we are calling it as center of mass of all particles as the center of box, center of mass of all molecules. No, because all molecules will give you same point, 1 point, and with respect to that we need to calculate. This is what we do not want. For individual particle, we want to consider that particle as a center of the box. With one particle as the center of box, no. Yes. So option fourth is correct. Why? This is my first distance, this is my second distance, or interchangeably this could be first, this could be second, and then we have to consider this center of mass of the two particles as the center of the box. So this is my box. That means we are standing on one particle and we are calculating which one is the closest one, right? Which one is the closest one? So this center of mass of two particles as the center of box. So option 4 is correct. Then question number 9, acceptance rates of the trial moves are very small. Then what we need to do? See, what we are doing, acceptance rate we have to calculate. So in a particular step we will move to some distance, right? Move the particles to some other distance, correct? From here to this particle it has gone in one step. If the distance is very high, that means the interaction energy will be changed by a very large amount, which may not be acceptable. That's why if such things happens and the acceptance of the trial moves are very small, then in that case we need to take small steps, because we know that by changing the position we are getting very high energy, and high energy means there is less probability of acceptance. That means if we want to increase the probability, we need to take very small step. So we should decrease the step size. That is the answer. But again, to tell you, the step set should not be very small, because if it is very small, that means for going from this point to this point, earlier I was taking one step, now I'll take 100 steps. What will happen? The number of steps that are required, the time that are required to reach that particular equilibrium value is very high. That means we need to decrease the step size if the acceptance rate is less, and we need to ensure that it should be close to 0.5, 50% acceptance. Then last question, shifting and the truncation of the interaction energy is done. As I said in this part, that we are calculating the interaction energies using different potential forms, just like this, LJ potential, right? And we know beyond certain distance, the interaction energies are very less. So particle is here, and this is how my potential is there. So you can see beyond certain distance, the interaction energy is very less. So this particle is here. I've had different particles at different locations, right? So this particle has particular sphere of influence up to which there are interaction energies. Beyond that, the interaction energies are very less. So if we calculate or not calculate, the difference in the interaction energy is very less. If we calculate the value, delta U value is not that, the change in the delta is very less, and the number of particles we need to consider will increase significantly. So to avoid that thing, we what we do, we are not calculating, or we don't calculate these interactions beyond certain distance are cut, right? This is called as truncated potential. So we are truncating it, and because of the truncation there is discontinuity here, so we shift it like this. So we shift the potential so that it goes to zero at this distance. So there we are using shifted and truncated potential. And why do we do that? To save the computer time, because if we calculate over longer distance, the interaction energy change will be very less, contribution to the interaction energy by that particle is less, but computer time it takes, right? That's why computer time we can save by truncation and reduce the numerical error. These are the two options. So this is about the questions and the portion that we have covered. If you have any doubt, please let me know. If there are no doubts, then we can close the session for today, right? So if there are doubts, please let me know, I'll be here. So if there are no doubts, we will close the session. Thanks to you for being there. We will end the session.